Thank you so much for the introduction and invitation to be here. So what I do is given, as far as I see it, my kind of overview of the current state of the art in the cognitive neuroscience of lucid dreaming. And this is part of a longer talk I usually give, so I'm gonna go through it, but I'll cut and maybe jump around a little bit just in the interest of time. But here's a quick outline, just starting off with some introductions and definitions to make sure we're all on the same page. I then want to give you a little bit of the history. I think it's really interesting in terms of the physiology of lucid dreaming, what we know about that. The literature really spans back 40 years, but there aren't that many empirical studies that have been done in that time. And then talk a little bit about some of the more current work that we've been involved in and other groups in terms of EEG and also fMRI. And then talking about how lucid dreams can be used as a methodology. I think, to my mind, this is one of the most interesting aspects of this field that I think has been also overlooked to a large degree, is how lucid dreaming itself can be a very useful method for empirical research on consciousness and within cognitive neuroscience more generally too. And I'll then end with a little bit of work that we've done, a little bit of an overview in terms of induction of lucid dreams, which I think will be a nice segue into Stefan's presentation. And so by way of introduction, and just thinking about this topic, it's interesting to reflect, I think, on this fact that isn't something we usually think about very often. First of all, just the fact that we all every night undergo these crazy hallucinations in these periodic intervals, where we're fully embodied and immersed in these worlds that have some connection with our waking lives, but sometimes very little connection. And to my mind, one of the most striking facts of this experience that we all have every night is the fact that we're completely oblivious to the fact that we're dreaming while it's happening, which is a really weird thing, I think, if you stop and think about it. Because again, often these experiences are very incongruent with the rest of our whole lives. I could be a different person. I could be on a different planet. My family members could be different people. I could be having just experiences that don't jive with the rest of my life. And this has been pointed out by a number of theorists. In fact, in the first edition of Sleep, the journal Sleep, Rechtschaffen wrote a whole paper on this and talked about the single-mindedness and isolation of dreams. It's one way of describing it, but we can say that while dreaming, we're unaware that we're lying in bed, we're unaware that what we're experiencing is a hallucination, and we're just generally unaware of the fact that we're dreaming. So in Rechtschaffen's poetic terms, we've lost the roadmap of our own consciousness. We've lost the capacity to be introspectively aware of ourselves and the state that we're currently in. And so that's the typical situation, but this really interesting exception is lucid dreaming. And so the basic definition of lucid dreaming, I think most people are familiar, but you know that you're dreaming while you're dreaming. So if you're aware that what you're experiencing is a dream while it's happening, then we would call that a lucid dream. So very simple. There are other aspects of consciousness that seem to go along with this, interestingly, and that's the whole area of interesting discussion, why that is, exactly how to put those things together. And the biggest ones are the capacity to control. So once you're aware that you're dreaming, you typically also are able to direct your actions or decide to do one thing instead of another, attend to one thing instead of another. It's kind of like, oh, here I am. Now what do I want to do with this state? And also episodic memory. So you regain memory of your waking life, including for intentions for things that you wanted to do in the dream, for example. But you just regain the continuity of memory. That's like a defining feature of human awareness and consciousness. So here's a quick example. It says, I was standing in a field in an open area when my wife pointed in the direction of the sunrise. I looked at it and thought, how odd. I've never seen colors like that before. Then it dawned on me, I must be dreaming. Never had I experienced such clarity and perception. the colors were so beautiful and the sense of freedom so exhilarating that I started racing through this beautiful golden wheat field, waving my hands in the air and yelling at the top of my voice, "I'm dreaming, I'm dreaming." Suddenly, I started to lose the dream. It must have been the excitement. I instantly woke up. As it dawned on me what had just happened, I woke my wife and said, "I did it, I did it. I was conscious within the dream state and I'll never be the same." So this is kind of a fun example. It does illustrate a lot of the things that we typically see, particularly from novice lucid dreamers in the sleep lab. So there does tend to be this sense of just kind of intrinsic exhilaration, you might say. Many people find it exciting to be able to recognize the state that you're in a dream, to be embodied within that dream and have that recognition of the true nature of your experience. And that often, of course, leads to awakening because you get an excitement response that then terminates sleep. But with time and training, people can learn to sustain these to have much longer experiences of lucidity in the dream state. So just a few quick remarks in terms of motivation. I think those of us interested in consciousness can already see a lot of interesting connections here, but I think there are other things worth pointing out too. From the science side, it's one of the points I want to try to convey is that this is a way for us to do psychophysiology of REM sleep dreams in particular that overcomes a lot of the limitations of what you might call the standard paradigm, in which we, of course, in the past, we would wake people up and gather a report after they wake up and try to line up that report with the physiology occurring during sleep before the awakening. But it's very, very tricky to be able to get alignment between that phenomenological report after awakening and the physiology as it was occurring beforehand. You can attempt to do that. We've done research on that as well. But as I'd like to show later, lucid dreaming presents a very powerful set of methods for getting very precise alignment between the psychology and the physiology during sleep. There are also a number of clinical applications, the largest of which is treatment of chronic idiopathic nightmare disorder. And in the US, I'm not sure about Belgium or Europe, but actually in the US, this is a huge problem. It's really remarkable. It's something like 6 to 7% of the adult population in the United States suffers from chronic idiopathic nightmares, meaning we don't understand why they're happening, but people have chronic nightmares. And as I'll briefly mention later, lucid dreaming presents some unique avenues for treatment in this domain. And now it's already being recommended as an add-on to traditional therapy by the major institutes in the US. The evidence is there are basically several small controlled trials at this point, so we need more work. All of them showing, for the most part, a benefit to including lucid dreaming in therapy, but we do need more work. So outside the science in the clinic, I like this term. I got it from Michael Pollan's book. He got it from someone else. I can't remember the original source right now, but the betterment of well people. We often tend to think about clinical applications, but I think we can also think about just ordinary people, healthy people. How can we continue to enrich our lives? How can we make them better? And I think this is an untapped domain for additional exploration of the human mind that we can all investigate together. Say, what more can we do with this state? Can we be doing something more with this state that we all go through every single night that right now we're pretty much just neglecting? And this is almost a kind of Silicon Valley view, if you like, but I think there's something to it. So dreaming is an underutilized resource. We're going to spend a third of our lives asleep. We're going to spend many years, if you total all that up over a lifetime, maybe 5 to 10 years, actually, 5 is a low estimate, dreaming. So the question is, how do we want to spend this time and what more might we be able to do with it, with our precious time? And there's many different kinds of things that have been discussed, like just sheer entertainment, rehearsal of skills, artistic and creative pursuits, and so forth. Okay, so with that introduction behind us, I want to give a little whirlwind tour of the the physiology of lucid dreaming and a little bit of the history of the science. So I think it's important to back up all the way to the 1950s and before, where there's a lot of skepticism about lucid dreaming, not only among scientists, but also philosophers. This is a philosopher, Norman Malcolm, 1959. The supposed judgment that one is dreaming is unintelligible and inherently absurd form of words. So people had a hard time with this concept. They thought, how can you be awake, in some sense aware in this way in which we're typically aware as when we're awake while asleep? It just seemed to be kind of an oxymoron, hard to understand. And this sentiment really persisted until the late 70s and early 80s, when the first empirical studies started to come out within sleep science. And what set the stage for those studies is this really interesting work, which is a whole interesting domain in its own right, about the relationship between the eye movements in REM sleep and ongoing dreams. So this was in particular work from Bill DeMint's lab at Stanford, which was occurring already in the late 50s, 60s, and into the early 70s. And they did a series of papers which were looking at the relationship between these rapid eye movements and other kinds of eye movements as well in REM sleep and the ongoing dream. So this is one of my favorite examples. They had a participant in the sleep lab who looked left, right, 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 about 12 times in a row. Here's the right oculogram on top, and then the left oculogram in the middle, and the EEG on the bottom. And this is something you just don't see in a sleep lab. I can tell you, for many nights, it's very rare to see this kind of stereotyped sequence back and forth like this of these scaled eye movements. They woke the person up and said, "Just now, what were you dreaming about?" And he said he was standing on the side of a ping pong table, watching a long volley of the ping pong ball going from one side to the other, back to the other. And so this is just one example, of course, but from this and many, many other kinds of examples, it was learned that the eye movements in REM sometimes do track where the dreamer is looking within the dream. It turned out to be a little bit of a complicated story. And originally, this was called the scanning hypothesis. And it turns out that, which was the original hypothesis, the scanning hypothesis said that all of the eye movements in REM sleep tracked where the dreamer was looking within the dream. And we know that that's not true. That's completely untenable. For example, congenitally blind people still have REMs. Decorticated cats have REMs despite lack of vision, all kinds of things. But we do know that at times, the physical rotations of the eyes indeed are tracking where the person is looking within the dream. And so this gave a young researcher in DeMint's lab, Stephen LaBerge, an idea to say, aha, I know how to prove the impossible dream. That is, when I become lucid in a dream, or when my participant becomes lucid in a dream, they can make a signal with their eyes by looking in a certain pre-agreed upon direction. It can be whatever pattern we want, and we'll be able to pick that up on our EOG while showing concurrently with polysomnography that they are in physiologically verified REM sleep. And that's indeed what they did in a sequence of studies. This was actually the first signal sent from a lucid dream to the waking world by LaBerge himself, just a single up-down eye movement marked with that U there, which by itself isn't particularly convincing, but this was the first one. The signal that became to be used as the gold standard is this signal here, which is one that we recorded in our lab at the University of Wisconsin-Madison. And it's a single pair of left, right, center eye movements. So all the way to the left, all the way to the right, all the way to the left, all the way to the right. And you get this very distinct signal in the horizontal EOG, which is larger amplitude than the background REMs, because again, it's very rare to get a case where you're looking all the way, like as far as you can to the left, and then as far as you can to the right, almost as if your eye is going to your ear. And to do it in this sequence like this gives a very distinct signal, which you can see very clearly just by eye. And so this is a signal from the dream world to the wake world to say, just now I'm aware that I'm dreaming. And this can also be used for lots of other aspects of the methodology, which I'll mention later. Here's just a few other examples from 6 different participants. You can kind of get a sense of what these look like. There is differences in morphology, but overall, You can see very, very clear across subjects. There's no question at all about what these signals are. And so this really set off a whole series of studies that began to be done throughout the 80s, 90s, 2000s, leading up to today. The earliest research was just looking at different aspects of autonomic physiology. So now that we have this method for marking when someone becomes lucid with the eye movement signal, we can ask questions. What's different about the lucid dream segmented by the eye signal versus the baseline REM sleep part? And one of the first things that was found from LaBerge and colleagues in Dement's lab was that these different measures of autonomic physiology are all elevated, not only during the lucid dream, but also in the 30 seconds leading up to the lucid dream. So here the vertical white line at 0 is marking lucidity onset. And you can see that this top left eye movement density is elevated in the 30 seconds prior to lucidity onset and stays elevated. Likewise, heart rate in the top right here stays elevated, respiration rate in the bottom left. And often you do get a skin potential response as well, which can be seen here in the bottom right. And that's indexing, we think, this excitement response that people typically get of realizing that they're dreaming. We don't always see this, and this is an area, I think, where a neurophenomenological approach can do a lot of good, because we can take these detailed reports from subjects and classify them. Say, based on the report, here's an instance where people became lucid and they were excited about it. Here's a set of cases where people became lucid and they were rather blasé about it. And do we see differences in the skin potential response? For example, there's lots of things that can be done like this. I think it's an exciting area for a neurophenomenological approach. But to summarize this early phase of research, LaBerge and colleagues found that lucid dreams tend to occur during sleep, which was, a big thing. Many people thought maybe these were brief arousals, but they found indeed that lucid dreams could be objectively verified to be happening in REM sleep. And then furthermore, tend to happen in the most activated stage of REM sleep, namely phasic REM, which go along with these measures of increased autonomic activation, increased eye movement density, increased heart rate, increased respiration rate. And so this all suggests that lucid dreams tend to be associated with increased activation, increased physiological activation. But of course, this raises further questions. Is this just a global activation of the brain? Or is it the case that there are regional increases in activity, as can be indexed either through fMRI, bold signal, or specific patterns of neural oscillatory activity, specific frequencies of EEG, for example. Both of these, I think, are still open questions. So there's been a little bit of work on these, and the papers have appeared somewhat sporadically over the years. Overall, unfortunately, the EEG studies are underpowered and tend to have methodological issues of one kind or another. And there's only been a few fMRI studies, so we're still in the early days of answering this question. But I just want to briefly mention what's going on the fMRI first, because even though there's only been a few studies using fMRI, there is, to my mind, something of an emerging initial, very preliminary consensus among the research findings. And so just briefly, this was the fMRI study that was done by Dressler and colleagues, which was published in Sleep in 2012. And this is the only study proper that looked at differences in bold activation during a lucid REM sleep dream inside the fMRI scanner while a lucid dream is happening. So a single subject, so unfortunately, this is a case report. Only a single subject in the study was able to fall asleep, get into REM sleep, have a lucid dream, and do the eye signal while inside the fMRI scanner. And they compared and they used the eye signal method. And so they were able to compare the time in REM sleep after the eye signal, validated lucid dreaming, signal verified lucid dreaming, to the baseline REM sleep segment. And they found that these different areas showed increased bold signal. You can see it includes a broad area of the anterior prefrontal cortex, mostly lateral, as well as the middle and inferior temporal gyrus, and both the medial and lateral regions of the parietal lobe, including the precuneus, which was actually where the maximum was. And so this set of frontoparietal regions and some temporal regions, it also goes into some occipital regions as well, as you can see there, is what they found from this single subject. But again, it's a case report, so important to keep that in mind. We used fMRI in a slightly different way, looking at individual differences. So I didn't mention this at the beginning just due to time, but in fact, if you look at the frequency with which people have lucid dreams in the general population, it's like 50% of people never have had one in their whole life. Another 40%, it's like it's 55, 45, it's about half or so. The other half have had at least one. If you look at that half that have had at least one, about 20% or so maybe have them every few months, and then maybe 1% are having them weekly, and then there's a very, very small percentage, maybe 1 in 1,000 or less than that have lucid dreams on the order of every single night. And these are often people that haven't even engaged in training, but they just have lucid dreams all the time, sometimes multiple times per night. And so the question is there anything different about these people in terms of their brain structure or brain connectivity? And that was the question we wanted to look at here. And so we recruited from many mass surveys a group of 14, I think it was, high frequency lucid dreamers that are having lucid dreams at least every other night, on the order of every other night or more. And we compared them to a group that was matched on dream frequency as well as age and gender. And we didn't actually see any differences in the structure of the brain, either with VBM or with cortical thickness. But we did see differences in functional connectivity in this group. And so we found that there was elevated functional connectivity between the anterior prefrontal cortex and the bilateral angular gyrus, as well as the middle temporal gyrus. And so you can already see that there is quite a striking convergence between this set of regions which shows increased connectivity in the high frequency lucid dreamers and that set of regions which was shown to have increased bold signal during a lucid dream. Just want to sweep through this. We didn't find any differences in connectivity within any of the large scale resting state networks, for example, visual network, salience network, DMN or frontal parietal control, but this network that we did find increased connectivity overlapped the most with the frontal parietal control network and also the default mode network. And so if you look at these two together, we do see this convergence of the anterior prefrontal cortex, the lateral parietal cortex, as well as the middle temporal gyrus. And we're interested in this and think it's at least promising and worthy of more follow-up research. Also, from what we know about the neurobiology of REM sleep and the neuroimaging of REM sleep generally. So this is a nice meta-analysis from Neer and Tononi in Ticks in 2009, which summarizes all the work that was done up to that point. And there were many studies done in the 90s using mostly PET imaging, comparing REM sleep to wakefulness. And you can see this really kind of amazing convergence here. The blue icons are showing studies which found decreased regional cerebral blood flow or glucose metabolism in REM sleep compared to wake. And the orange or yellow icons are showing increased regional cerebral blood flow or glucose metabolism in REM sleep compared to wake. And you can see that this same set of areas, including the anterior prefrontal cortex, lateral and medial parietal cortex, and middle temporal gyrus, all have suppressed activity in REM sleep compared to wake. And so that also fits with these findings on lucid dreaming. Perhaps these regions which are typically suppressed in REM sleep regain activation once you become lucid. So that's at least a hypothesis that we can continue to follow up on. And so again, just putting this all together, The setup regions are all typically deactivated in REM. They show increased bold signal during the case report of a lucid or case study of a lucid REM sleep dream inside the scanner. And individuals who have lucid dreams with very high frequency show increased connectivity with these regions. And also, from what we know about what these regions are involved in, things like executive attention control, metacognition, and so forth, it also makes sense as well. So I think this is an interesting, although very preliminary convergence. I think the largest thing that myself and many others in the field want to see next is a group level fMRI study. That's the major desiderata at this point. Very difficult to do, very time consuming, very cost intense, but I think that's really what we need next to be able to move this forward. Group level study with a sufficiently large sample. Even better than that would be to have multiple recordings from those multiple participants, so that you can also look at repeated observations within individuals. So that's kind of the fMRI side. Just to swing back to the electrophysiology and EEG side of things, here things are much more mixed. I think we're much more in the dark on this side. And so there's really only been about 4 studies in the peer-reviewed literature since the early 80s, and they all found different things. So they all have a different purported neural signature of lucid dreaming, if you like. So there's a study by Ogilvy, which found increased alpha, and that wasn't replicated by other research later. There's a study by Holzinger-LaBerge, which found this difference in the ratio of frontal to parietal beta. Study by Voss, which found increased gamma at the frontolateral electrodes. And a study by Daudet et al. Looking at narcoleptic subjects who had lucid dreams, which found decreased frontocentral delta. You can already see that many of these studies have very few electrodes, very limited spatial sampling of the scalp, 1 electrode, 4, 6, and often they don't even overlap with the same regions. And so it can be very difficult to compare these as well. The one that's gotten the most attention, and somehow this paper by Voss in 2009 only had 3 subjects, by the way, but this is kind of what's just like the default view, you might say. And you read about it in the line at the checkout stand at the grocery store, that lucid dreaming equals this increased gamma activity at frontolateral electrodes. This is the original finding right here from the original paper, showing this electrode here, F7 and F8, showing increased 40 hertz power in the lucid REM part compared to the baseline REM sleep. However, many people didn't seem to notice that there's a big problem with this study. And the biggest one is that they didn't actually correct for the myogenic component of eye movements. So every time you move your eyes, whether in REM sleep or while awake, you of course get these large corner retinal dipole offsets, to do with the rotation of the eye. But your muscles, which are controlling your eyes, particularly the lateral oculus muscle, lateral rectus, also contract. So every time you move your eyes, you get a contraction of those muscles, and that leads to a spike in the EEG. These are called often saccadic spike potentials or pre-saccadic spike potentials. And unfortunately, this paper didn't actually correct for the myogenic component of eye movements. And this is a big concern because, namely, just anyone who does EEG, looking at where that finding is right there in the paraorbital electrode, should be immediately concerned about this. But also what I noted before, that lucid dreams have increased eye movement density. And we know that from the early papers from LaBerge and others. And so if that finding does hold up, that lucid dreams have increased eye movement density, this particularly becomes a concern about whether this reflects eye movement density or whether it reflects something at the cortical level. And so this is a recent paper, actually it says under revision there, but we're now in press at Sleep. And we wanted to look at this critically. And the first thing we did was actually replicate this finding. So the finding having to do with eye movement density and lucid dreaming, so which we did. So we found that lucid dreams, replicating those early findings from LaBerge, were higher. So eye movement density is higher in the lucid REM segment compared to the baseline segment. And then we looked critically at this frontal gamma effect. And what you can see here is that the top trace is showing the EOG. So before every one of these large corneoretinal dipole offsets with the eye movement, you see this spike here. And those are the pre-saccadic spike potentials. And if you look at the time frequency transform, you can see this increase, particularly in high frequencies, this transient burst overlapping the 40 hertz range. And very consistent across subjects, and it localizes precisely to that frontolateral area. And so what we did was we actually we built an algorithm to identify every instance of the spike potentials, and then we removed those from the time frequency transform. So you compute a time frequency transform and then only compute over the non-contaminated segments, which is what we did. We found that using only a regression eye movement technique, which is what's similar to what Voss did, we replicate the frontal 40 hertz effect, also with current source densities. But if you remove the spikes or if you use ICA, we don't see any difference in frontolateral 40 hertz activity. We did some exploratory analyses of other EEG markers, and we found that there was this broad reduction in delta activity as well as 12 to 35 hertz in the beta range during the lucid segment compared to the baseline REM sleep. And also we saw that there was reduced coherence, but this is really a reflection of this decrease in power in the delta range. And also, I think really interestingly, we see that there is increased complexity in the EEG signal during the lucid REM segment as well. So two different markers of complexity, both Limpel-Ziv and the normalized permutation entropy, both show very consistent increases in complexity in lucid REM compared to the baseline REM sleep. In fact, I think all but one of the subjects showed an increase across two different measures. So we think this is also an interesting finding, but all this is still rather exploratory with, our sample was larger than previous studies, but still is 14 here. So, it's still not a huge sample. I'd like to see this replicated. One of the big points though is that these findings here, it's not like lucid dreaming is just this some other state in which baseline REM doesn't have these levels of delta or beta or complexity. In fact, if you look over time within lucid REM and you look over time within the baseline REM, what you find is that there are valleys and peaks of activation. And so you can look at histograms, for example, and what you see is that they overlap. And so this suggests that these markers are not unique to lucid dreaming. They're different markers, we think, of activation. And so when activation tends to be highest in lucid REM, those are the moments when people are most likely to become lucid. And interestingly, for reasons we don't fully understand, those different markers of activation sustain during the lucid REM segment. So all of this plays into this larger debate and discussion that's happening about what is lucid dreaming. And to our mind currently, the most parsimonious explanation or interpretation of all the data is that lucid dreaming is REM sleep through and through. It's not some mixture between waking and REM sleep. There's no evidence that it's a mixture between REM sleep and waking physiology. All the classic markers of REM sleep are maintained in lucid REM sleep, as you can see in this table here, such as the classic decreased muscle tone, the decrease in occipital alpha, the REMs, and also H reflex. So a marker of spinal cord inhibition, which is unique to REM sleep, is also preserved. So all the different physiological markers are preserved. And this hybrid view is really predicated on this gamma effect. And furthermore, since we don't think this gamma effect is cortical, we think it has to do with this increase in eye movement density. That really removes the last leg to stand on for this hybrid view. And so we think that REM sleep, the current interpretation is that lucid dreaming is a form of REM sleep. And so it's a special and unique form, but nevertheless, it is physiologically defined REM sleep. And so I'm just noticing how out of time I am. And so I want to kind of just very, very quickly, in maybe like 1 or 2 minutes, take you through these last couple of sections, if that's okay. And so lucid dreaming is a methodology. This is my favorite example from LaBerge. You know, you can count to 10 seconds and make an eye signal while you're awake. You can do that in a lucid dream. So this suggests that perception of elapsed time is actually the same across waking and dreaming. We did a recent study in which we wanted to look at smooth pursuit eye movements. So we know it's impossible to imagine, a smooth pursuit. So humans can't engage in smooth pursuit for an imagined object. No one had looked at this for dreaming, and it's impossible to do that without lucid dreaming. And so this is just one example of how lucid dreams can be used as a methodology within cognitive neuroscience, because may sound like kind of a quaint idea. Well, do you get smooth pursuit for dreams? But in fact, it plays into a very, very important discussion about the nature of the human smooth pursuit system and whether it's guided by perceived motion, apparent motion, or actually a physical motion stimulus. And so we train people to do different kinds of tracking tasks by tracking the tip of their thumb in a lucid dream, either this way with a line or a circle. And then skip over this and just show you, this is what the line task looks like. So the green is marking smooth pursuit, and the magenta is showing these saccadic catch-up motions. So during wake, you get this sustained smooth pursuit. And likewise in dreaming, you get the sustained smooth pursuit. And then imagination, you get these characteristic catch-up saccades. People can also trace infinity signs in circles, clockwise, counterclockwise, which is very cool, has its own offshoots, that people can trace shapes. It suggests they can also trace letters, for example, which I think has implications for many of the things that you all are interested in terms of communicating with people who are aware, but nevertheless paralyzed and so forth. I'd love to talk more about that. Putting all the data together, we see that dreaming and imagination are virtually identical and very, very different from imagination. So you can separate them with the Bayesian classifier with over 97% accuracy. So anyway, this has a whole bunch of interesting implications for how we think about smooth pursuit, how we think about the nature of the imagery in REM sleep dreaming, and studies like this are only possible with using lucid dreaming. So it really does open up a whole new way to do research as a methodology, which I think is underappreciated and very interesting and can be very useful for cognitive neuroscience. The big picture is that lucid dreams allow us experimental control over the REM sleep state in a way that's completely impossible any other way. And we get these precise temporal markers using the eye signaling method. But of course, the major challenge is we need to have ways of inducing it. So there's cognitive techniques. There's a technique called wake back to bed, where you wake up an hour before and you go back to sleep. There's electrical brain stimulation, which has been tried in a few studies, which actually doesn't work, but at least it hasn't been very effective in the studies so far, even though I think it is an interesting direction to go in the future. And there's also these different kinds of cueing devices shown here, like a sleep mask, which flashes red LEDs over your closed eyes, and then you see flashing lights in the dream. You can use that as a mnemonic or a memory cue to recognize your dreaming. And then the last one I want to talk about is pharmacology. We did this large-scale study, double-blind, placebo-controlled, in which we looked at the effect of an acetylcholinesterase inhibitor, galantamine, on lucid dreaming, together with these other techniques. So the mnemonic techniques, the cognitive training, as well as wake back to bed, combined with the pharmacology. How well can we do? How effective can this combined technique be? We knew galantamine worked already from a lot of pilot work, but we wanted to give a precise quantitative figure to how effective it can be. So people slept for about 3 REM cycles, about 4.5 hours. They woke up, they took 1 of 3 counterbalance doses of galantamine. So this is within subjects. They all did this on 3 different nights. They stayed awake for 30 minutes and they went back to sleep for the experimental nap segment. And then they woke up and gave us a report. And we found this whopping, huge, substantial linear dose-related increase of galantamine on lucid dreaming frequency. So The baseline here is showing what you'd expect from this group based on no intervention at all, based on their reports of the previous 6 months lucid dreaming frequency. G0 is the placebo combined with these other techniques of wake back to bed and cognitive training, about 12%, the half dose 4 milligrams of galantamine, about 27%, and the full dose 43%. So 43% of people were able to have a lucid dream with this combined technique of galantamine plus these other techniques of lucid dream induction, which is humongous. And it's the largest, most effective technique that I know of currently for having a lucid dream. And so this, I think, really does start to open up a dialogue about how this can be open to a wider audience, particularly in clinical and scientific settings, at least to start. So if you want to learn more, there's also a review paper that I wrote with Martin Dressler in Neuroscience and Biobehavioral Reviews that I'd point to. And with that, I will end. So thank you so much.